Uh, okay, well, I'm sure they're very smart. So, and yeah, please interrupt with questions. I'm going to keep it quite informal. Today, I'll just give you an introduction to quantum spin liquids and insulators. And then tomorrow, we'll talk about how you extend that to metals, different types of metals, and maybe even superconductors. And my last lecture will be about strange metals and SYK model and all of that. Okay, so to begin with, so let's imagine we have some antiferromagnet here, where these S's are spins on the sides of a lattice, could be a square lattice or a triangular lattice for definiteness. So SI squared, it's spin a half, so this is 3/4. And we want to know something about the actual ground state. Now, if I took literally the triangular lattice or the square lattice, we know the ground state. And the ground state is the same as the classical model, which is an antiferromagnet that I showed you with spins pointing anti-parallel on the square lattice and on 120-degree angles on the triangular lattice. But let's imagine there's some longer range couplings or something else. And we explored the possibilities for spin liquid states, the simplest spin liquid states that you can imagine on these lattices. So there's two ways of doing it. And it's, we learn a lot, actually, we've learned a lot by doing it both ways and comparing the results, because everything is going to be approximate. So we can do it, for example, by writing each spin. I'll drop the I index in terms of what are called Schwinger bosons. So this will be B dagger alpha, sigma alpha beta, B beta. So we have a constraint on each site, that B dagger alpha, B alpha, sum on alpha is 1. And these are the Pauli matrices. So this means there are two states. So the spin up state is the same as adding the Schwinger boson or spin up on a boson vacuum. And the spin down state is the same as adding the Schwinger boson to spin down on the vacuum. Now, because the number of bosons on each side is 1, these bosons can't really move. They can only flip their spin. You could equally well, and everything would be exactly the same if you wrote them in terms of fermions. If these were fermions, that's also allowed. And so now the spin up state will be 1 fermion on this side. And the spin down state will be fermion down on each side. And again, you have sum on alpha, F dagger alpha, F alpha equals 1. All right, now if you were to exactly solve the problem, it doesn't matter what you use, you will get the same answer. But we're not going to exactly solve the problem. We're going to solve with some approximate method. And we're going to get very different answers. They're going to look very different. But what has been learned over many years of work is how, in fact, the answers are not different. We can now connect them up. And once we connect them up, then we have some deeper understanding of what's going on and some confirmation that our approximate theories are actually pretty good. And of course, you have to check them with numerics and so on. So I think, a lot of progress has been made on these problems in the last 25, 30 years. I will tell you a little bit about that, especially those models that correspond to nearest neighbor interaction on the square or triangle lattice being the dominant interaction. Okay, so how does this analysis proceeds? Well, what you do is you just insert this in here, and you write down some path integral. And then, excuse me. I'll do the boson case first, and then I'll talk about the fermion case. So how far can I go as far as the camera is concerned? I should stop here. You can, no, but in the. You can move the camera. Okay, good. All right. Okay, and lower, yeah, you can see down here, right? All right, so you just insert this into this Hamiltonian, And you can see you get a 4 boson or 4 fermion term. Let me just stick to the bosons. And then we apply a usual trick of Hubbard-Trutanovich transformation. And so then you can rewrite this theory, the partition function of this theory, as an integral of a bond field, which sits on every bond. So for every bond on the site of the lattice, there's a Qij. And then there's going to be a Lagrange multiplier, which is going to insert this constraint. And then there's going to be a path integral over the B. So the other complicated looking object, but it's got this following general structure. So there's going to be minus 0 to beta d tau of some Lagrangian. And that's going to have things like Qij squared over J, and then J, Qij, B dagger I alpha, B dagger J beta, epsilon alpha beta. This is what you get if you have anti-ferromagnetic interactions. Epsilon alpha beta is the anti-symmetric tensor. And then you get a constraint that imposes B dagger I alpha, Bi alpha is 1. Okay, so that's almost the exact representation. Factors of 2, I probably got wrong. I should say this commercial announcement is I've written a book which is coming out in a week or two, which has all the factor of 2 correct, I hope. So please look up the book. All right, so this is the path integral that you have to evaluate. And the way we are going to do this is, of course, just do the B path integral. This thing looks, oh, I'm sorry, I forgot the most important term. There's also the fact that imposes the B commutation relation. So Bi alpha dagger D Bi alpha d tau. That just tells you that B's are canonical bosons. In any case, the B's are quadratic here, quadratic here, quadratic here. So it's possible to do the path integral and get some complicated functional of Q and lambda. All right, so I won't write it out, but this can be written then as dq d lambda of exponential of some effective action of Q and lambda. Okay, so you can work this out. You can know exact expressions for it. And then you can solve the saddle point equations, and we're going to do a saddle point expansion. We're going to solve this equation ds dq equals 0, and ds d lambda equals 0, and then do a path integral about that saddle point. Okay, so the rest of this lecture, and maybe a little bit of the next lecture, is just telling you what happens, what kind of saddle points do you get, and what does this subsequent path integral, which we also have to understand. We can't just stop at this level. We want to understand the path integral completely, and what do you get? And what emerges from these path integrals is, in fact, a theory of different types of spin liquids. Okay. All right, so, these spin liquids are rather different on the square and the triangular lattice. And it's the square lattice, this triangular lattice that turns out to be easier to understand because it gives you a gapped spin liquid immediately, whereas the square lattice is a little more complicated, but also the more important one as far as the cuprates are concerned. Okay, so everyone with me so far? Okay, so you solve these equations in the triangular lattice or the square lattice, and what do you get? Well, there's a question of a sign, but you can always choose the sign and correctly. You have to look up my notes. You basically get Qij. The average value is independent of Qij, and it's something, let's say, Q bar, just a constant. And also similarly, you get I lambda average value, is just some lambda bar. So basically, this means that to zeroth order, you can just replace this Q by a constant. and this lambda by a constant, lambda bar is q bar. And so now you have a very simple theory for bosons. You just have a Hamiltonian for the bosons that you can write down, which has an extremely simple form. So now you get a Hamiltonian. Which looks something like this. H is just basically sum on the lattice sides from Q bar, B dagger I alpha, B dagger J theta, epsilon alpha beta, plus lambda bar. That's it. Okay. So this is just a free boson Hamiltonian, and you can diagonalize it by a Bogoliubov transformation. So as a function of momentum, for appropriate parameters, you'll get some dispersion. And let's imagine you've chosen your parameters as the dispersion has a gap. Okay. So now you found, now you're very excited. You've got some mean field state, and you can really work this out in some detail on the square lattice and the triangle lattice, get all the numbers. You found a saddle point, which has a gap of some boson, and this boson carries spin a half. So this is a particle which has spin a half and charge, Q is different from something else, charge is 0. So this is what we call a spin-on. Okay, so you got a spin-on which has no charge, has a spin a half, unlike the originals. These spin operators have integer spin, they change spin from up to down. This B dagger alpha carries spin a half. So this is exactly the spin-on that I showed in the pictures in the previous lecture. And here we have a simple mean field theory for the spin a half particle, which is a boson. So from those pictures, I couldn't tell, is it a boson or a fermion? Here, by my choice of working with the bosonic decomposition of the spin operator, I've got a mean field theory for the spin-on with a gap. Okay. So we seem to have found some spin liquid state. This is a state that preserves spin rotation invariance. It has a spin a half excitation. And so that's very exciting. All right. So now the question is, what does this mean? Is this stable? On what kind of lattices can you find it? And is this the only other fractionalized excitation around? Okay. So the short answer, which I will try to give you, is that this is stable on the triangular lattice, but not on the square lattice. And on the triangular lattice, there are other excitations that are around. There's also, which have gaps. And these excitations have a one-to-one map with what's now known as the toric code, although all of this was discovered well before the toric code in the early 90s. So it's what's called the Z2 spin liquid, which I'll try to explain. And in addition to the spin-on, there's called a Vison, and there's also some fermions around. So all of that extra stuff comes from going beyond the saddle point. So really, we have to understand this whole integral much, much better. This is a mean field theory, but it's not by far not the end of the story. Okay. So let me first begin by showing you why the story is different between the square lattice and the triangle lattice. Okay. So for that, we have to understand the structure of this action of the fluctuations in here. Okay. And in general, this is some complicated action with all kinds of terms, and it seems that possibly if you computed it, you wouldn't see any structure. But there is some deep structure in there, and that structure is associated with the fact that this original path integral has a gauge symmetry. Okay, so if I look at this original path integral with the Qij, then this path integral here, including this term, that's also important. So this path integral has a very important gauge invariance, which is exact, which we really have to think about more carefully in trying to understand the fluctuations of this about the saddle point. So what is that gauge symmetry? Well, you can check that if I make the following transformation, I take bi alpha and I multiply it by e to the I phi I of tau, any arbitrary function of tau and position. And then I take qij and I multiply it by, to make this invariant, you can see what you have to do. Qij e to the I phi I plus phi j of tau. And then finally, there's also this term that's going to include some phi dependence because of the time derivative. But you can compensate that by this Lagrange multiplier here. So lambda sub I will go as lambda I plus or minus, I don't know, d phi I d tau. So if you make this transformation for any phi I of tau, you can see that this path integral, this action remains invariant, doesn't change. So this must mean that this action here must also be invariant under these two transformations. So this is a very complicated action, hard to write down, but whatever it is, it must be invariant under these transformations if you did your path integral over B correctly. Okay. All right. So there's some very complicated set of constraints that are coming in from here. And the important fluctuations, the important thing to look at for now is really what happens to the Qs. And in fact, even forget about the time dependence, that's not so important, but look at the spatial dependence of the structure of the action of the Qs. So now if I have some saddle point, and in general, when I'm doing the fluctuations about the saddle point, I will write down my Qij. It has some amplitude, Q bar plus some delta Q, which is going to fluctuate. And then it also have a phase factor, which let me look up my notes now. So I have to put this right. Yeah, I called it theta. Okay. Okay. Yeah, I call it theta here, big theta. Theta of ij. And so this is the amplitude, and this is the phase fluctuation. And I have to do the path integral over here over both Q, delta Q, and theta. Now, all of the interesting stuff, now you can see that delta Q doesn't care about this gauge transformation, only theta does. And all of the interesting things I'm worried about have to do with this gauge symmetry. So I'll just forget about delta Q and just look at theta. So now theta has a very simple gauge transformation. Theta goes to phi I plus phi j. So now I can, to do it on a general lattice, it's useful to go to momentum space. Okay, so I'm going to erase some of this now. Okay, so what I'm going to say is that, so let's see if I do it for the triangle lattice. Okay, I'm going to take three vectors here. This is E1, E2, and E3. And so for each of the E's, I will have a theta, which will be P, where P equals 1, 2, 3. And I'll take the Fourier transform of it rather than writing in real space variables. And I'm going to put this theta at the center of the bond. Okay, so the theta lives over there, then I think the Fourier transform, I'll get 3 of them. Okay, so then you can look up the gauge transformations of the theta P. So theta P of K under gauge transformation will go to theta P of K. Minus, 2 phi of K cos K dot EP over 2. Phi of K and cosine of K dot EP over 2. So this tells me that if I look at the effective action, which must be gauge invariant, it's got to be sum of various terms, sum over P and P prime of theta P of K times cosine theta P prime over 2 minus theta P prime of K cosine theta, sorry, not theta P, cosine K dot EP over 2. Where? So the fluctuation must be quadratic because you're expanding about a saddle point. So the gauge invariance in very general, yes. For the triangle lattice, 3 are independent. Yeah. So this is the action you'll get. So you get 3 terms between any 2 pairs. This particular combination is invariant under this gauge transformation. Okay. This is just the usual gauge transformation of electrodynamics. It's just you're working on a complicated lattice. That's all. All right. So now you have to ask, is there any particular, can we get a 0 energy excitation in this fluctuation? In other words, is there some value of K at which this thing just vanishes? All the terms vanish. And you can easily check on the triangle lattice, there isn't. There never is a 0 energy mode of this. So then the triangle lattice, this thing, these theta fluctuations are fully gapped. So at least perturbatively, this tells you the whole structure is very stable. But on the square lattice, there's only 2 values of theta, of P. You don't have 3 neighbors, you have only 2 neighbors. And then there is a value of K for which both of these vanish. So on the square lattice, if I chose K equals pi pi, and then I just had E1 is just 1, 0, and E2 is 0, 1, then this vanishes. And so what you will get then is S P, S the effective action, there's going to be two values of theta. So it'll become essentially K equals pi pi plus some small q. So you will find that this is equal to this S is equal to theta x of q times qy minus theta y of q times qx squared. So when qx equals qy equals 0, it just vanishes. Now, of course, you recognize what this is. If I just relabel theta x as ax for a better notation, then this effective action for the A is just dx ay minus dy ax. So that's like the flux term or the Maxwell term for some U1 gauge theory. And this is appearing at pi pi because of the fact that there was a plus sign over here. So you can basically, essentially, you're taking your square lattice and you're assigning a charge structure plus minus the charges you're giving in terms of these gauge fields to the boson. So the boson on this sublattice of charge +1, the boson on this sublattice of charge -1, and that's related to this pi pi. And then when you take the low energy limit of the fluctuation, the phases of the Q, the fluctuation of phases of Q behave exactly like a U1 gauge field. So this tells you that the low energy theory of fluctuation on the square lattice is electrodynamics. So there's a long range force, there's a photon, which is a massless particle. So this theory, in addition to having on the square lattice, in addition to having this massive spin-on, this gapped spin-on, bosonic spin-on, also has a gapless photon. It's got a photon excitation, which has a linear dispersion with omega equals ck, like any other photon. And that emerges from looking at the structure of the fluctuation about the saddle point. So on the square lattice, we are not done. We have a theory of gap spinful particles, but we also have a photon floating around. And that gives you long-range forces, so we have to really understand what the low-energy theory is before we can conclude as what's going on. So there's a long saga there on how to understand what this photon does and various non-perturbative effects associated with the photon, which I'll try to summarize. But before we go there, let's go back to the triangle lattice. So for the triangle lattice, if you try to do this, you never find a photon. Basically, you can never find, you can just take this quadratic form and look at its eigenvalues. You never find at any momentum k any zero eigenvalue. Whereas here there is a zero eigenvalue and q equals 0. Here there's no value of k, where this thing will give you a zero eigenvalue. Right. Other than the one associated with the gauge mode, of course. But the energy itself won't vanish. All right, so for the triangle, for the square lattice, we have to pause. For the triangle lattice, we have hope. At least perturbatively, there is a gap, not only in the bosons, but also in the Q fluctuation. The Q lambda path integral, if we start to do it, we find that there's a gap. So everything should be controlled, at least in some larger limit where this saddle point becomes exact. Okay, yes? There is a spin liquid state where everything is gapped. That's so far, at least for large enough n, yes. Yes, so that, yeah, so the magnetic order will appear when this spin-on, when this goes to 0 and this spin-on condenses. So when this thing goes to 0 and you post-condense here, then you will get that mode, the magnetically ordered state. That's also a possibility, but we are imagining that, okay, for some reason you've got a spin gap, and then we're trying to understand if this is the spin gap state stable. Okay, and so far we're seeing it's stable. At least perturbatively, but in this particular path integral. But now but there's a deeper question: is it always stable, non-perturbatively? And what is the other phase that you get if you keep fluctuating a lot, even while the bosonic spin-ons are gapped? Okay, that's described by a Z2 gauge theory. I'm not sure I'll have time to derive that, but my book goes into that in some detail. Okay, but yeah. Yeah. No, of course not. I said that at the beginning. Nearest neighbor, we know the answer. So if you did this for nearest neighbor, honestly, I think this gap will vanish. and you'll get the triangle of the 150-degree state. But now let's put in second neighbor, third neighbor, some other interaction. I'll put it on the Kagome. I think the Kagome is where this is some chance of actually working. There's evidence for it in numerics. This is gapped. There's no broken symmetry. And then you do this kind of fluctuation analysis, and you never find any gapless mode. Okay, everything is gapped. The Q, the lambda, the B. Of course, there's a trivial gapless mode associated with the gauge invariance, but that, of course, you have to factor out. That's not a physical excitation. Yeah. What is the intuition you're asking? Yeah. Well, so the point is that, yeah, I think that's a very good question. So let me try to give you some intuition. This is, if you would just close your eyes and turn the crank, this is what you conclude. But if you were smarter, you would do the following reasoning. So the Q's on the square lattice are on these bonds, okay? So now we ask the question, is there some gauge transformation, some long wavelength transformation, which leaves all the Q's invariant? So you have a saddle point. You ask, here's my gauge transformation. Is there a gauge transformation that leaves all the Q's invariant? They don't change at all. Well, there is the gauge transformation where if you put phi equals plus, phi equals, A on this side, and phi equals minus A on this side. If you did that transformation, then every bond, every Q remains invariant. It's a bipartite lattice. On the triangle lattice, there's no way to do that. So on the triangle lattice, if you try to do that under this transformation and leave every Q invariant, what you find, suppose you put plus here and minus here, and plus here and minus here, then these bonds are in trouble. Everything else, all the other bonds are okay. These bonds have charge 2. So in this theory on the triangle lattice, you try to get a photon, but in addition to getting a photon that you will get on this lattice, you get a charge 2 boson or charge 2 Higgs field. And that's like a Higgs field that breaks the U1 gauge symmetry down to Z2. So that's why this is sometimes called a Z2 gauge theory. Okay. You can make that more explicit, but I don't have time to go into all of that. I'm more interested in the square lattice, and I'll come to that later. Excuse me. Okay, so, but let's talk about the triangle lattice a bit more. So this is where I shouldn't have erased all this stuff. So if I go back, I integrate out the bosons, and the triangle lattice, I have an exact representation of the path integral. So I had the SMDQ, B lambda, exponential of minus some action of Q and lambda. And what I argued that there was a saddle point, Qij equals some Q bar plus some delta Qij, and then lambda I is some lambda bar plus I delta lambda or something. And then I did the path integral over delta Q and delta lambda, and I found that everything was exponentially correlated and gaps that well behaved in this path integral. Okay, is that the end of the story? The answer is no. If you want to really do a non-perturbative calculation, you should ask, are there any other saddle points? This is one saddle point, but there could be some other saddle points which have a slightly higher energy, but there could be so many of them that when you summed over all saddle points, they became more important. And that's the answer to that is yes, but it takes a while before they all become important. And what describes those other saddle points are precisely the Z2 gauge theory. So the question is, are there any other saddle points? So this is the saddle point we're working with. Are there any other saddle points? In other words, any other solutions of ds dq is equal to ds d lambda equals 0. Are there any other solutions of this other than constant? Okay. And the answer is yes. And the analysis here is very similar to something you've already done probably in Landau-Ginzburg theory of superconductivity. When you get the Landau-Ginzburg action, you ask, what is the saddle point? The saddle point is uniform superconductor. But then Abrikosov came around and showed, oh, there's another one, which is a vortex, which has a slightly higher energy, but the vortex has quantized flux, and then as you heat a superconductor in the costless Solis condition, the vortices you can destroy the superconductivity. So we want to ask a similar question here. Is there some vortex-like saddle point, which has only a finite energy? Even the vortex in the Landau-Ginzburg theory has a finite energy because of the London penetration depth. So is there some finite energy excitation, other saddle point? And the answer here is yes, and I'll show you what it looks like. So the finite energy excitation looks something like this. And this is something we have checked numerically. You can find this thing, both on the triangular and the Kagame lattice. And recently, one of my students, Yang-Ting Tang, is also working on finding it for Rydberg models. All right, so here's my triangular lattice. So we found a uniform solution. So we found a uniform solution, okay? But now I'm going to give you a non-uniform solution, and it's going to have a center that will be the core of this object. And so let's imagine the center is over here. And then I'm going to draw a branch cut. It doesn't matter where I draw the cut, but I just draw it, and it goes off to infinity. Really, it goes off to another endpoint somewhere where I have another vortex. So that's infinitely far away. And then what do I do? Well, if the Q, let's imagine Q bar is positive. That's some gauge choice, positive. So far away over here, Q is equal to Q bar. So if I go really far away in this direction, Qij just equals to Q bar. So out at infinity is equal to Q bar, except if I cut this line, here the sign of Q is -1 on every bond that cuts this. Okay. So now, if I look at what's called the flux, if I take the product of any plaquette, the flux, the number of, I have to cross this line twice. If I take any closed loop, I have to cross this line an even number of times when I'm far away. And since the energy only depends on the flux, this branch cut is invisible. So if I'm out here at infinity, I see some of the Q's having a negative sign, but that's invisible because the flux to any loop is still plus, is the usual one because I have to cross the line twice in any loop. So in fact, I can move this wherever I want. That's just a gauge choice. Okay. So out here, if I'm sitting out here, Q will just equal to Q bar, except from somewhere it'll change sign. But where will it be important? But there are some loops where you can cross an odd number of times. But those are the loops over here. If I take a loop like this, and that loop crosses an odd number of times, that's going to cost me some energy because the uniform solution has zero flux. This is the product of the signs. But there is some flux here. That's going to cost me energy. So this is very much like the Abrikosov vortex. But unlike the Abrikosov vortex, which has a current flowing in one direction, this does not. This preserves time reversal symmetry. There's no broken time reversal symmetry. It's the sign has changed. The phase is still real. Everything is real. So there's no currents or anything. You don't break time reversal, but there's an energy cost. So what you'll find is that the magnitude of Q, if I plot as a function of R, the magnitude of Q, well, it'll be equal to Q bar really far away, but down here it might get a little small or something. Very much like, again, in an Abrikosov vortex, in the core of the vortex, it will go down. And this length scale over which this happens is just the inverse of the gap of the spin-ons, you can see. Okay. All right, so this is now a stable object. Once you suppose for some reason the system landed in this saddle point, it can't get out of it. There's no local arrangement. You'll have to erase this line out to infinity, and that will take you an infinite amount of time to erase the line. So this is what now called a super selection sector. There's no local operation. There's no local operator that will remove this object. It can only annihilate with another object far away. And that's actually also true for the spin-on. The spin-on, as I showed you in a picture in the first part of my talk, you create a spin-on by creating a pair of spin-ons and moving them infinitely far away. Once you have a spin-on, no local operator can get rid of it. So what we have found are what are called two super selection sectors. You have the ground state, then you have the spin-on sector, and then you have this sector, and this is called a Wison by Spencer and Fisher gave it that name, although discovered by Reed and Chakrabarty much earlier. And in the toric code, this is what you call the M particle. And the spin-on, in this case, a boson, is what you call the E particle of the toric code. So amazingly, out of this completely standard Schwinger boson calculation, you're starting to get the full structure of the toric code. And I guess I have to mention, we did this calculation long before the toric code. We didn't know about it. It didn't even exist when this was done in the early 90s. All right, so now we have, in fact, a second emergent particle. So this thing can move around. It has finite energy. It has some kinetic energy also. It can move around. And when you get lots and lots of these Wisons, then you know the saddle point is really bad. You have to sum over all the Wison saddle points if they get very low in energy. And you can have what's called a confinement transition, where you lose the spin liquid and you get something else. Okay, I'm not going to talk about that, but you can read about that in my book, The Confinement Transition. All right, so we have the M particle, or the spin-on. And the spin-on was this B object acting on the ground state, really. No, not the vacuum. That's the spin-on. It's some, you had the Hamiltonian with the Bogoliubov transformation. When you create an excitation out of that, you get your spin-on. And I showed you pictures of that in the first part of my talk. But you notice another beautiful thing here, that there is now, these spin-ons and Wisons, they're bosons on their own, but they're mutual anyons. So there's some anyonic statistics that doesn't exist in the real world with any particle. And that it corresponds to the fact that if I take a spin-on around the Wison, that spin-on will have to cross this once, and pick up a -1 from the fact that the hopping of the spin-on is controlled by the Q's. So spin-on going around a boson has a -1 sign. Okay. Then finally, you can imagine also creating an excitation, which is the bound state of a spin-on and a boson. So the bound state of a spin-on and a boson, in modern language, this is written as follows. So suppose I take a spin-on and a boson far away, and I bring them close to each other. Excuse me. So the spin-on is called the E particle in the toric code language. So fusing them or bringing them together is saying E is written this way, E cross M. And that forms a new particle, which is called the epsilon in the toric code. So that means you just take the saddle point and you just add a free spin over here. And they're just sitting here. And there's for some reason they attract each other and they form a bound state. Whether they actually form a bound state or not, who knows? Depends on all kinds of details. But if they formed a bound state, there will be some other excitation, which is called the epsilon particle. Now, another beautiful thing, this epsilon particle is a fermion. So we started with Schwinger bosons. We looked at saddle points, and we found the spin-on excitation and the boson excitation, and we formed a bound state. Magically, we found a fermion. And you can check that easily, again, by counting these. If you take this bound state and move it halfway around another, so if I had an epsilon particle here, it's got a branch cut going out to infinity with a B next to it. And there's another epsilon particle. It's got a branch cut going out. And then I take it around this. I'll pick up a -1 because the epsilon has a B inside it. There's also a B dagger sitting here and a B dagger sitting here. So this B dagger, when it crosses this, will give me a -1. And so this thing is a fermion. So I have, in principle, another excitation in this spin liquid, which is a fermionic spin-on, because it also carries spin, because it has a B dagger alpha sitting next. So there's a boson sitting here and a boson sitting there. And the bound state of the boson and this boson is a fermion. Okay. Now, what is this fermion? So what we understand today, by detailed analysis of a lot of these theories, this fermion, you remember I started the lecture by saying I could have written my spin operator in terms of fermionic spin-on. I could have used this fermion. So what people have been able to show, I guess I have to end, right? That this fermion is this. So that's a rather beautiful thing. You start out with the Schwinger boson approach. You can reproduce the full structure from the Schwinger fermion approach, and vice versa. You can do it the other way too. So in fact, in the end, it's what we call a Z2 spin liquid, which has the same anion content as a toric code. And you can get it two different ways in two different saddle point theories, and they're all shown to be the same. Okay, there's somebody else coming in? Okay. So sorry, maybe one or two questions. Yeah, so that's a totally different approach. You will do exactly what I did with the fermion. You will start with fermions, and then you'll find a boson. Then the bound state of the fermion and the boson will become the boson.
So how many particles?
3. So you stick to one approach. You stick to with the boson approach, you get the boson first, and then you get the boson, then you get the fermion, and that's it. You're done. If you do the fermion approach, you get the fermion first, and then you get the boson, then you get the boson. You're getting the same state with two different descriptions, but it's the same state, at least in terms of without a phase transition between them. One may be better numerically, one may be better than the other. That will depend on which particular Hamiltonian you're looking at. Yeah. This is all two-dimensional. Everything I'm talking about is two-dimensional. This cannot happen in 1D. 3D is more complicated. Yeah. 3D, you have to look at lines, and there are more, the structure of topological phases in 3D is more complicated, but also kind of theoretical because that has never been seen in any experiment.
So actually, there's an online question.
Yeah.
I guess it's just question about notation. The question is, why is the saddle point Hamiltonian not Hermitian with both B dagger, but not B minus B? I think
I forgot to add the
Yes.
Hermitian conjugate.
yeah.
It is Hermitian.
Yeah, I
So-
hope the question is answered satisfactorily. Yeah. Okay, so in any case, so let's thanks Professor Sachdev for this wonderful talk, and please be reminded that tomorrow afternoon we will have the same talk at either this room or the neighboring room. You will see, and tomorrow will be